Hi, welcome to Fundamentals Friday. This is a follow-up video from my previous one about measuring input offset voltage and some issues I had with an analog devices part. If you haven't seen it, click down below and you'll be able to watch that. It's a 30-minute video of me mucking around measuring some input offset voltages. Great fun. But today we're going to do something related, which we'll get back to on the breadboard and solve our problem from last time. We've got op-amp input bias currents today. What is an op-amp input bias current and why is it important? Well, let's take a look at it. You've got your basic op-amp here. It doesn't matter what op-amp it is, they're all going to have what's called an input bias current. Now, you're used to dealing with an ideal op-amp. Now, an ideal op-amp, of course, one of the rules for the ideal op-amp is that no current flows into the input pins. But of course, in practice, that's complete bullshit, because you're going to have some current flowing into or out of, we'll get into that, these input pins on this op-amp, and that's called the input bias current, and I've labeled that here IB plus and IB minus. Now, a data sheet for a typical op-amp will usually only show the input bias current as one figure IB, they'll typically call it. They won't actually specify different input bias currents for the positive and negative. And that's where we'll get into later is the input. There's two parameters to do with input bias current. One is the input bias current itself, IB. The other is IOS, which is the input offset current. And that is actually the difference between these two. But we'll get into that in a minute. Now, this input current in practice can range anywhere from femtoamps, a really schmick precision instrumentation grade op-amp might have, a few tens of femtoamps input current. Or for a really fast wide bandwidth op-amp, they don't care about the input current, so it's going to be a couple of microamps. They're going to optimize the internal architecture for that op-amp. They don't care about the input bias current, they're going to optimize that for bandwidth and slew rate and all sorts of other things. So there's a pretty big range there in the input bias current. So how does it work? Well, let's take a look at the input circuitry, or the basic topology of the input circuitry for a bipolar operational amplifier. So this is not a FET input, it's a bipolar input op-amp. And you'll notice that we have two input transistors here, both NPN going into a current source. It's a current mirror configuration, and I won't go into all the details of, well, any significant detail of input op-amp architecture. That requires a whole separate video, but suffice it to say, look, these inputs are connected directly to the base of these transistors here. Your positive and negative input on your op-amp over here goes into these transistors. So naturally, you're going to get some base current flowing in there and in there as well. And there's ways to lower that. Of course, if you use a FET input op-amp, well, FETs aren't effectively, right? They're a field effect transistor, no input current. But in practice, there is. In theory, there's not in practice. But this is a bipolar operational amplifier. Probably the most common one on the market, although FET ones are pretty darn common as well, CMOS ones. And there's other ways to lower this input bias current as well. They can actually use a Darlington configuration here so that your input bias current is lower. It was still using the bipolar manufacturing process, but there's issues with that in terms of bandwidth and all sorts of things, which I won't go into. And the other way to do it is what's called a bias offset operational amplifier, or a bias offset input. And what they do is they actually put in here a current source in there and in here as well, so that that biases the transistor instead of the input bias current. So in theory, it cancels it out and you can get very low input bias currents from the input, but not zero. They almost never, well, in practice, you can never get down to zero bias current. So every practical op-amp, regardless, even if it's input bias compensated, is going to have some form of input bias current, or IB, and it'll be mentioned in the data sheet. Now, these bias currents, they can be a real pain in the ass in precision applications, and there's quite a few different ways it can screw you up. Let's take a look at the first problem, is your source impedance of well, your source impedance, okay? That's the series resistance of your source. Let's say it's 10K. It might be a typical value for some systems. And if our input bias current is a very low 100 picoamps, right? That's a pretty good op amp, very low input bias current at 100 picoamps, okay? Then our error that we're going to introduce in our system without ignoring everything else, offset errors and all the rest, is going to be 10K times that 100 picoamps, because the 100 picoamps is flowing through that 10K resistor. We've got a 1 microvolt offset already, 1 microvolt error. And it doesn't sound like much, does it, 1 microvolt? But if you're dealing with a precision system, then that can, like a strain gauge or something else you're dealing with, that can be a real big deal, because these errors get multiplied by the gain of your op amp. So it can screw you up right there. Just be careful. And 100 picoamps, that's a very low one. So imagine if your source impedance is like a meg or something like that, and your bias current's even higher, you can get millivolts of error. Watch out. Now the second problem we've got is errors introduced into our gain network and our feedback resistor network for this thing. Now what happens, let's take this inverting op amp configuration, and here's our input voltage, that's our output of course, and let's ground this input here and see what happens. Now because the input, the non-inverting input down here is also grounded, and once again we go back to our ideal op amp properties. We're assuming our input offset voltage, remember we're not talking about offset voltage yet, is 0. So the difference between here and here is going to be 0. Remember, due to op amp action, the op amp does whatever it needs on the output to ensure that the two inputs are exactly the same voltage. If your input offset voltage is 0, which we'll assume. So this point here is also 0 volts. It's also grounded. So there's no current flowing through R1 there at all. So, but we still have an input bias current. Remember, we always have that. You can't get away in this practical configuration. So where does it come from? Well, it can't come from through this resistor here, because Ohm's law says 0 volts across that resistor. Doesn't matter what value it is, this R1, no current flows through it. So all of the current must come from RF here. In this case, it flows around like that. So all of our input bias current is flowing through RF. And you might see the problem already. Usually, you want on an op amp, you're going to have some sort of gain, times 5, 10, 50, 100, even 1,000, depending on your, your circuit application. Well, that means RF your feedback resistor has to be a large value. What do you get when you have a large value resistor with a current flowing through it? IB, even a very small one. You're going to get an offset error introduced over and above your VOS, which is another figure on the data sheet, your input offset voltage. This is in addition to whatever that is. So this is where input bias current can be a real pain in the ass for these precision applications. All of that bias current flows through RF. So how do we solve these input bias current issues? They're a pain in the ass for these precision applications. How do we get rid of it? How do we cancel them out? Well, let's have a look at what we've got here. IB plus and IB minus, one goes into the inverting input, one goes to the non-inverting input. So they're essentially opposite currents. So you can actually cancel them out. Now let's go back to our original non-inverting configuration here, and we've got a simple voltage follower, okay, with our source impedance RS in here, whatever value it is, causing the error due to the input bias current flowing through it. Well, we know that the other input has an equal and opposite, or should have an equal and opposite input bias current. How do we cancel it out? Very easy. We just put a feedback resistor in there equal to, let's call it RS2, equal to the value of RS. So if IB plus and IB minus are equal values except opposite, because they're going into opposing inputs of the op amp, I won't go into the internal details of it, but then you can cancel them out by having a resistor in the feedback loop like that. And how do we solve this inverting op amp configuration here? Well, essentially exactly the same thing. Instead of this going to ground down here, we have a resistor in there going to ground. So we're going to get our input bias current, and we can actually cancel them out like that. Now let's call this RB, and what value should RB be? Well, it's a standard formula. It's actually RF in parallel with R1. Now, I won't go into how you actually derive that. It's not actually that hard if you want to go into the details, but I won't waste the time doing that. But that is a basic formula, and this is a very common thing that you'll see in a lot of circuits. You might have wondered why. Well, why does it have this resistor in here? Is it protecting the input somehow? No, it's to do with the input bias currents in these precision circuits. And of course, if you've got a very large gain here and RF is much greater than R1, then you can just say RB equals R1, because the parallel combination of RF on top of that, and to a rule of thumb, to an order, if you've basically got a gain of 10 or more and RF is 10 times R1, you can generally say RB equals R1, near enough. So that was too easy, right? We've fixed our input bias current. No big deal, just whacking a resistor in there and you're right. Unfortunately, doesn't work like that in practice, because the input bias currents are not matched. These transistors are never a matched pair. You're never going to get precisely the same value. There's some op amps that get really, really close, but in practice, it's not going to be zero, just like the input bias current itself, regardless of the topology used, is not going to be zero either. And that's where this IOS comes in. The input offset current is the difference between IB plus and IB minus. So there's actually two parameters there that you have to look at. Not only the input bias current itself, like the input bias current could be really low. It might be 10 picoamps, for example. But then if your IOS is 100 picoamps, for example, then, well, geez, it's all over the shop. There's no way that you can choose a resistor bias value that's going to work. You might fluke it. You might be able to tweak it for an individual chip or an individual circuit, but just as choosing a generic value to do it, no, you're not going to be able to do it. Unfortunately, it is just a problem with these op amps. If you're doing ultra precision applications, yeah, you'll have to trim these things to take into account the input bias currents. And on top of that, then we've got our voltage offset as well. So you could get to a point, depending on your particular op amp you've chosen, that IOS could actually swamp your effective IB, or vice versa, or there's a combination of the two, and it can get really ugly. But on top of that, you wouldn't know it's even worse? Well, you might have a rail-to-rail op amp. Now, I mentioned right back at the start, I think, that the input bias current can go either direction. Now, on a standard bipolar op amp like this, or on a FET input op amp, for example, you're typically only going to get your input bias current going one way. But on rail-to-rail op amps, they're internally biased and they've got different configurations. And I won't go into the transistor configuration of a rail-to-rail input op amp, because there's lots of tricks. They can actually vary and stuff like that. But basically, it means that current can also flow out of these pins as well, depending on the common mode voltage you're operating at. So if this is 0, for example, you might have a curve like that where your current can be, bias current can be positive and negative. So this can be IB here, positive and negative, and at some transition point where you pass through it, you might end up going, current may flow out of these pins back out and ruin your day. It can get really ugly. So there's all sorts of problems. You've got IB, you've got IOS, you've got V offset, you've got whether or not your input configuration, your topology, your circuit, and all sorts of stuff. Is there an easy solution? Nah, afraid not. So in practice, this can be a really big issue, even for circuits that you might not think are that critical. So you've got to keep an open mind, watch out for it, just in case you get caught. I mean, depending on what supply, this can change with supply voltage as well. The common mode here, that's V common mode here, depending on what input configuration, whether or not you've got an input bias compensated or rail-to-rail op amp, the supply voltage, all sorts of stuff, and which configuration you're using, your source impedance. Oh, and we haven't even mentioned temperature. So how do you know if your op amp has one of these input bias compensator values? Well, you're typically going to get a plus minus IB value like that. They're usually not going to give it for your input offset, but plus minus IB, that's a dead giveaway that the op amp you're using, even though they may not tell you, is input bias compensated. So you can see how complicated this is already getting. And really, you know, we're not even throwing VOS into the mix much, the input offset voltage, which the gain is going to get multiplied, which is going to get multiplied by the gain of your op amp here. And it can get really, really nasty. So if you see any input offset issues, they will typically be a combination of the real input offset voltage, which is a separate parameter, VOS, an entirely separate parameter on your data sheet up here, but it can also include your input bias currents. And that's what we saw in the previous video. If you haven't seen it, link it down below. So let's now go back to the breadboard from that previous video and see if we can reduce or eliminate or compensate for these input bias currents and see how it affects our final output offset error. And just a quick background to our previous video, and you really should watch the previous video. It'll be linked down below if you haven't seen this. Otherwise, it may be a little bit confusing for you. But basically, we had an analog devices AD8628 op amp with times 100 gain in the non-inverting configuration, and we were getting an output voltage which was higher than just the expected offset voltage here. Now here's the actual circuit we've got. We've got 1K going to ground here, we've got 100K here, total gain of 101. We're going to call it 100, near enough. And the input offset voltage of this particular op amp is supposed to be around about 1 microvolt. So we only expect sort of around about 100 microvolts on the output here, but this is our output voltage, and we're getting over 300 microvolts here, and this is our supply voltage. We're using a split supply here, so the ground point is actually in the middle, so it's plus minus 2.5 volts. But our output voltage is higher than what we expect from just a typical device. And technically, yes, it is within spec, because here it is, input offset voltage VOS there at 5 volt supply is a typical value of 1 microvolt, but it could be as high as 5 microvolts. So that would translate to 500 microvolts on the output here. But as I said in the previous video, that's not actually the case. This op amp is actually typically 1 microvolt or less, and I've tried multiple op amps, and that error is coming from somewhere else. Well, guess where? Input bias currents. And if we have a look at our data sheet here, you'll notice that, as I explained before, there's a figure for IB there, input bias current, and input offset current right here. Here it is, the 8628. It actually gets higher with the quad package, by the way. That's just to do with the process technology that they're actually using. They've got 4 of those on the one die, and it's different. So anyway, we've got the single one, the 8628. Input bias current, typically 30 picoamps. It could be as high as 100 picoamps there, but you know, we are going to get the typical figure down in here. So, 30 picoamps. Let's have a look. Is it a coincidence that our output is just over 300 microvolts here? Let's do the math, shall we? 30, if IB here, let's ignore this input here. Okay, let's ignore the non-inverting input. Let's just look at the inverting input here. If our input bias current, let's assume it's going in to the pin, then if it's 30 picoamps going in, you remember before, if we ignore the V offset, then there's no voltage drop across this resistor. So all the input bias current, that whole 30 picoamps, typical, is coming through that 100K resistor. So let's do the math here. 30 picoamps, there it is, times 100K equals 3 microvolts. So we're getting 3 microvolts error just due to the current going in there, the input bias current into that inverting input there. But the gain of the op amp, of course, is 100. So we have to multiply that by 100, and of course you get 300 microvolts. Look, 300 microvolts or just over. Is that a coincidence? I think not. Well, it's not going to be the entire story, but it is certainly going to be a lot of the reason for this. And by the way, if you haven't seen the previous video, this does change with supply voltage. So if we drop the supply voltage down, you can actually see it change significantly and even go negative like that. You remember what we were talking about with, oops, sorry, it should only go to 2.7. There we go, 2.7. It's almost going negative there. So that does change with supply voltage, as I mentioned previously in the video earlier. Now, of course, that's not going to be the only reason, but it's going to have a significant effect on that. Of course, our V offset is going to come into it, and the V offset is going to get multiplied by the gain of 100 as well. And then we haven't taken into account the input offset on the other pin and stuff like that. But there you go. That is going to be a very significant reason for it. So the previous video, yes, I mean, I've done this stuff before, but it's actually been, you know, I don't know, 7 years or something since I last touched this sort of stuff. So I forgot that the error term is going to be coming through the 100k resistor here, and it didn't help that the analog devices datasheet actually shows these exact same values in a typical example test circuit. So, you know, I just overlooked it. That can easily happen to even somebody who's done this stuff before. And I made the assumption that it was only going through the 1k, which is incorrect. All of that bias current is going through there. That's why I knew that I could have put an additional bias resistor in here like this, but then I knew, you know, I sort of did the math in my head as I was going along, and I went, oh, it couldn't make an effect. I could make that one 1k, of course, as we talked about. It should be 100k in parallel with 1k, but, you know, it's going to be pretty close to 1k. So we can put that in there, but I think we'll find if we do that, and we will do it in a second, that it will change this value. This value will actually change. Now let's actually get an average of that, shall we? There we go. It's pretty close. Let's call it 300. Spot on to 300 average. So what we'll do now is we'll just put a bias resistor in here, and we'll find that it'll likely change. I'd be very surprised if it doesn't, but it's not going to null out to 0 because we've still got the V offset plus other issues, and then the supply voltage as well, and this is a rail-to-rail op amp as well, and as I mentioned, and all that sort of stuff sort of comes into effect. And we haven't even mentioned, ta-da, the elephant in the room, which is the input offset current, IOS. Look at this, a typical value of 50 picoamps. Look at this, so it's actually higher than the input bias current. So even if both inputs are matched precisely, so even if we had VOS equal to 0, which it's not, but let's assume it was, and both these input bias currents were identical, and we put our 1k bias resistor in here, this IOS is still going to screw us up because we have an uncertainty there between the two inputs, IB plus and IB minus, of 50 picoamps. So you just don't know. You don't know what this chip is going to do until you actually build it up and test it. Alright, so I've now soldered a 1k resistor in there, bias resistor into the non-inverting input there, so we should be able to compensate for that claimed input, typical input bias current. So let's switch the supply in here, 5 volts, and look, it has actually dropped. There you go. It's dropped from 300. It's all over the shop. There's a bit of noise on there. Let's get an average of that. There you go. Let's say it's dropped to 180. Oh, I think it's changing because it's probably still something still a bit warm there, perhaps from my soldering iron. You've got to be careful of that. That can be a trap for young players when you're measuring critical stuff like this and you've just soldered it. Oh, the chip could be hot, the components could be hot, whatever. Anyway, it's dropped from 300 down to 200. So that is a change, which I would have been surprised if we didn't get any. There we go, it's 240. So it's not quite, you know, it's changed by 70 microamps, but it's still, as you can see, even with the input bias resistor in there, properly designed, it's still not happening. So how can we solve this? Well, of course, we could put a pot in here and actually tweak that out and null it out, but that's not actually a solution for the final circuit I want. So what we're going to have to do here is drop these values, because as I said, all that bias current, IB, looks like it probably dominates. I basically, what I want to do is reduce, fix this circuit so that the input bias current really doesn't have an effect. It's dominated by the VOS term there. So let's lower these by an order of magnitude, and we should see, let's leave this 1K in, well no, actually I'll take out the 1K, right? I'll take out the 1K, I'll short it back down to ground. Let's lower these by an order of magnitude. So I'll put 100 ohms and 10K in there, and we should find that 300 we got before drops down to, you know, in theory it should drop down to 30, right, if VOS doesn't come into it, but it could drop down to 100 or something like that. But we should find that we'll get better than what we're getting here now. And there you have it. It dropped, but not by a huge amount. You know, we're only talking, what average, you know, 240. It's dropped like 60 microvolts or something like that. Not a huge amount when we dropped these by an order of magnitude. But then again, we don't have that bias resistor in there. So let me add 100 ohms in there. And bingo, there you go, with a 100 ohm bias resistor in here. That's, look, we're getting, it's a bit noisier. I got a huge resistor on there. It's probably picking up something, but let's get an average on that. There we go. It's dropped down to an average of like 50 or 60 microvolts. So we've effectively, you know, really gotten down to just what we expect with the V offset voltage there. Because on a typical chip like this, I expect it to be slightly under 1 microvolt. So like 0.7, which would be this digit here, would be 1. So if we had 1 there, it would equate to a V offset of 1 microvolt because of the gain of 100. So the fact that we're getting around about 0.7, if in theory we've nulled out both those input bias currents, and we're not sure if we have. I mean, that's the thing with this, right? We don't actually know what we've, well, we know we've achieved something, right? We've trimmed this thing down so it's better, but we don't actually know what the exact culprit was, because this is a rail-to-rail op-amp here, so we don't exactly know the topology. Add on that this is a chopper amp as well, so there's going to be input switching current and all sorts of stuff to do with that. And this isn't just your regular op-amp, by the way. It's an input, I've done a whole video on chopper amps, which I'll link in down below, as I did link on the previous video. So, you know, we've tweaked it by lowering these values and adding in our proper bias resistor. And, you know, we can probably say now that VOS dominates, but does it? We don't know, because we've only got one sample of this chip. I'd have to do like, you know, 10 samples to get sort of meaningful data to see what the exact culprit is. We don't know whether the input bias is flowing in or out of either of those pins. You know, it's just crazy. And, well, let's see what happens if we change the supply rail. Here we go. Oh, sorry, I got to switch off my average mode. It's not a rolling average, it's a average over time there. So let's start back up at our maximum supply rail of 5 volts. Let's say we're getting 100. There we go, that's different to what, anyway, it's jumping around a bit. It's a bit noisy, but we drop in and look. Look at that, folks. It's going negative now. There you go, which is okay. It's to be expected. But there you go. Now we're down at its minimum supply rail of 2.7 volts, and we're getting basically a negative. We've gone all the way from positive up to, hang on, bloody multimeter. There we go. Average. We've gone all the way from positive to negative there, because this is a rail-to-rail op-amp. As I said, the topology we've got allows currents to flow either way, and in combination with V offset, which also could change over the supply rail range. So a common mode range is different, and our bypass decoupling as well, which we saw made a difference in the previous video. All these things combined make this a little tricky circuit to actually null this thing out completely over the supply range, but I'm pretty happy with that. By adding the bias resistor in there, we've done a pretty good job. I mean, I don't care if it fluctuates plus minus like that over the supply voltage range. You kind of expect it to do that really, as long as it's within your acceptable margin. I mean, before when we were getting 300 microvolts, in some chips I was measuring we're getting 500 microvolts. That clearly wasn't acceptable for my purposes that I want it for. So, but this sort of range, you know, plus minus 100 microvolts or 1 microvolt essential V offset combined, then hey, that's just fine. And then if we install a 500 ohm trim pot as the bias resistor here, you'll notice that we can actually tweak it. Let's get our average there. Watch, see, it's stable. Now I can tweak this thing. Look at that, not a problem at all. So you can actually tweak your input bias currents. You can null them out, but then you've got to do that at a particular supply voltage, of course, and common mode range. But of course, if you start changing your voltage rail here, then you're going to find that that setting is, look, no good anymore. So yeah, it's only going to be valid, that particular bias current, for a particular supply and common mode input range. Oh, and by the way, if your bias resistor here is actually too large in value, then noise can become a problem, thermal noise. So you may want to actually bypass that with a cap. And for those curious about the bypass caps, I've removed both of these and I've put a 0.47 mic directly across the rails like that. Once again, we're back to our 100 ohm input resistor there, and there's our offset voltage, or our equivalent offset voltage with our 5 volt rail. And of course, if we take that down, it's just going to drop again and again and again, and we'll probably find that one sucker there go a bit negative, down at 2.7. And it makes no difference if we leave both those caps in and put a 0.47 across there as well. It's still not going to fix, in quote marks, the issue. So what we've got here is a chopper amp. Its internal architecture is unknown to us. It uses some ping-pong patented architecture that analog devices have come up with. It auto zeros and chops and does slices and dices and makes your bread for you and does all sorts of things. So yeah, it's going to, we're not going to get a consistent well, a VOS and or input bias currents that can go in either direction for both of the inputs over the supply voltage range here. So what are you left to do? Not much. You either put up with it over your supply voltage range, or you fix it at a particular voltage range, or you choose some other op amp. It's up to you. And for those curious if we're actually able to measure the input bias current on here, well, let's give it a go, shall we? Not particularly easy, but I've hooked up my Keithley Pico ammeter. There it is, and that at 5 volt supply rail, it's the 1 nanoamp range, so we're talking picoamps there. So 16, 20 odd picoamps into that non-inverting input. That's through that 100 ohm bias resistor, and if that's at 5 volts. And if I lower the voltage, that's 4.5. We'll probably see it change. It's a bit noisy there. This isn't the lowest noise setup. I'd have to dick around a lot more to get lower noise. That's 3.5 volts. There we go. We're getting almost down to 0. Will it actually go in the opposite direction? 2.7. Yeah, it does. So there we go. That's a 2.7. It's actually gone the other way. Ta-da! So there you go. I hope you enjoyed that follow-up Fundamental Friday to the previous video. And if you like the concept, give it a big thumbs up. And if you want to discuss it, you know where to do it. The EEVblog forum, or you can leave comments on the blog website or on YouTube. Catch you next time.